Oh, it's being live streamed. Oh my gosh. Do I have anything?
Yes.
Oh, it just told me recording is in progress.
I
Hold on. Let me wait.
Okay.
1 second. How do I let me pause share really quick just because I want to go and here. I'm gonna clear out some of my tabs just to make this look better.
Okay.
Okay, resume. All right. Can you guys see the thingy again?
Mhm.
Okay, sounds good.
Okay. So then now we'll get started. So, hi everybody. My name's Emily and I'm a senior,
I'm Isabella, and I'm also a senior.
and we'll be your host for this webinar.
We'd like to wish you all a happy Valentine's Day and welcome you to the National Biodiversity Teach-In.
And today we're here with Jocelyn Wagner. Jocelyn, go take it away.
All right, hi. So I'm Jocelyn, and thank you guys for the introduction, and thank you to the NBTI team for inviting me to come present. I'm super excited. I currently go to UIC. I'm in my third year as an undergraduate, and I study Earth and Environmental Science. And my presentation today is just going to be about some basic info, my experience, and what the future holds for me and other environmental science students. So let's get into it. I'm sure many people in the past have picked up a rock or maybe been to a national park or some other sort of like nature area and wondered like, how did this happen? How did this get here? And geology is how we answer these questions, geology and geoscience. It's a very broad field, and through that, we can solve a lot of these kinds of mysteries. So, yeah. So what is geology and geoscience anyways? It's the study of Earth. It is Earth history, Earth's materials, Earth's processes, and Earth's natural forces that help shape the landscape that we see presently today. And geology doesn't just reference things that happened in the past. Geology and geoscience is still ongoing. So, in however many, many, many years, um, geoscientists of that era will be looking back on our time period now and trying to piece together like how did this landscape shift during our lifetime. So, some key areas of geology are plate tectonics, fossils, natural disasters, climate science, and of course, rocks and minerals. Just as kind of a fun fact, a lot of people have been to the Grand Canyon, and in the Grand Canyon, you can see a lot of these like striped layers of rock. So each of those stripes represents a layer of geologic history. The way that I like to think about it is similar to tree rings. If you have ever seen like the inside of a tree trunk and it's got the rings, and those rings represent like the years that it's lived. These layers are a very similar concept, just over a much, much larger scale. And each of these layers represents a piece of history. So, why am I interested in this in the first place? I have always liked to get into the mud and get my hands dirty and be outside. And I grew up with nature around me like my whole life. My hometown, I lived very close to a park, and that's this park down here that is Lord's Park. And it was always really nice to have quick access to that. And it's really cool to wake up, look outside, and it's like, oh, look at this like beautiful green space. And then also, my grandparents used to live very close to the Mississippi River near the border of Illinois and Iowa. And every now and then we would go out there, and the river itself it was always really nice. It's very serene, very peaceful, and very, you can look at it and just think like, wow, this is so cool. Like, and it was really neat to grow up around that. Um, that there was also a very large emphasis on recycling in my upbringing, and why it's important, thanks to my father. Um, so I think that that was also very influential, just the fact that having people around me that cared about the environment, it really made an impact. And I took AP Environmental Science in high school and I really, really enjoyed it. Prior to getting into this field, I wanted to be a dentist, and I have since pivoted. And I think that this, while dentistry is rewarding in its own way, I think that this career and this discipline kind of resonates with me a little bit more. And then I've included some images here. Through UIC, I've discovered that this is a really great STEM career for those that enjoy these outdoorsy activities. I mean, you're not required to be outdoorsy in order to be an environmental scientist, but it definitely does help. And I've met some really great people. I've met some really great friends and people that I think will kind of be around me for a long time in the foreseeable future. And it's also really easy to make connections at through my department at UIC as well, because quite honestly, we're a bit of a smaller department. Sorry, in comparison to, say, computer science or the medical studies programs. But because of that, the department is very much like a little village, and we're all, you know, everyone knows each other. You have the opportunity to really connect with your professors, and there's a lot of job opportunities working for professors, and there's also research opportunities, which I have just started this semester, research with one of the faculty members at my school. And I think that it's very cool that because our department is so small, there's a lot less pressure on you to go up and ask your professors these things, because for the majority of your time at UIC, you and those professors will be on kind of a first name basis, which is really neat. So over here, I've just got some pictures. 2024 was a big year for me in terms of outdoorsy activities. I went camping with some friends. That picture's over here. And then this is our dog companion, Gurgi. And then I also visited Minnesota to visit one of my very close friends from middle school. And this was our dog companion, Blue. So today I'm gonna kind of just cover like four topics: minerals, rocks, fieldwork slash research, and then also like how can you turn this sort of thing into a career. So minerals. What is a mineral? How do you identify a mineral? What's the difference between minerals and rocks? Bunch of questions. So I would consider a mineral as the building block of our planet. Minerals make up all of the rocks and sediments on Earth. Minerals are all over the place. There are minerals in your phone. There are minerals in a museum gift shop. There are minerals in the concrete outside, and there are minerals, or there could be minerals in the paint in your house. They're all over the place. They're easy to overlook because you don't really think about them. I mean, when you think of a mineral, you might think of like a rose quartz, which is the image I've got here. That's probably one of the more famous minerals. And when you imagine it, when I visualize rose quartz, I imagine like a nice little sample sitting on someone's desk, and it's like, oh, this is such a cool like mineral. It's so pretty. But you don't ever really think about like what are the applications of this anyways. So, minerals are super important to humans. We have industrial minerals, which are like raw materials for manufacturing, which would be, for example, there are minerals used to make screws and used to make drywall. Um, there are ore minerals, and these are the sources of valuable metals. So these minerals would be useful for metallic products, such as pipes. And then we have gem minerals. These are the ones that you'll find in crystal stores, in gift shops, in necklaces. These are kind of the pretty ones that everyone knows about. And for me, when I picture minerals, these are the ones that I think about. So, like amethyst, emeralds, garnets, diamonds, I would classify those all as gem minerals. So how do they form? The most common way that minerals form is through crystallization. So crystallization just means the solidification of a melt, and it just means that it precipitates from a solution. So what does that mean? In these three images here, I have kind of a diagram of how that happens. So in this top one, we've got our liquid solution that could be just any combination of elements that are in a liquid. Over time, that liquid starts to solidify, and all of those elements kind of mold together. And then, so that would be this second image here. And then they keep molding and building on top of each other. And then that's how you get this third image. Um, you can kind of think about this like a real world example, which I feel like is like somewhat common, is if you have your faucet where you get your tap water from, over time, unless you're really, really good about wiping down your faucet, and I might be exposing myself here a little bit, over time, it starts to develop this like white ring around it. That's actually crystallization. So there are minerals in your tap water. One of the most famous one is fluorite. And over time, those minerals just accumulate and accumulate and solidify, and then eventually you get that white ring around it. The common name for that is a lime scale or lime, but I believe the actual um, scientific name is calcium carbonate. Then there are other methods too, such as like precipitation from a gas, but these ones are less common. Crystallization is kind of the big one. So, and then there are a couple ways that minerals form, and here's some fancy vocab for you guys. There's anhedral and euhedral. Anhedral is represented by this picture down here, and that means that it's grown in a very tight, confined space, and so it doesn't get to develop like a nice crystal face. Crystal face just means like that would be like the sides of a mineral. So, as you can see in this image, the crystals and the structure are it's very Mod Podgy, kind of messy looking. It just kind of looks lumpy. We would classify that as anhedral. And then euhedral means that it was grown in an open cavity. It had plenty of room to expand and develop, and it has good crystal faces. So that would be this image over here in the bottom right. That would be euhedral. Um, so you'll notice these square blocks are pretty like almost perfect cubes. And they kind of reside in this little rock sample right here. So these cubes look really nice, really shiny, really clean cut. While they may have been polished just for the sake of photography, these cubes actually grow this way. This is very accurate to how these minerals actually form. And so it's not uncommon to go out into the field, and once you get your rock hammer out and you're trying to like test minerals, um, and eventually some of them will break into these like cubed shapes, which is really neat. No one has to go in and cut them to look like this. This is just how they naturally break or naturally form as well. So some properties that we use to classify minerals are color. Color is not the most accurate all of the time because some minerals have different color variations. So for example, this top pink one right here, this is a fluorapatite. Um, and then this blue one over here under luster, is also a fluorapatite. So you can't always rely on color to be like the definitive way of identifying a mineral because sometimes it can be deceiving depending on which color variation you have. Um, the next way is through streak. So what streak is we have little porcelain slabs. We call them streak plates. And how it works is you take your mineral and you pretty much just try to scratch the plate with the mineral. Um, you might notice a lot of geology requires some breaking of your samples, and it's kind of a common theme that in order to know what something is, we have to kind of rough it up a little bit. And so, yeah, you take your little mineral and you try to scratch it on the streak plate, and then whatever color the streak is, that can help lead you to your mineral identification. Um, the streak is not always going to be the same color as the mineral. Sometimes it is, but other times you can have like a red mineral and then it leaves a black streak, and then you're wondering, you're like, how does that happen? The surface is red. That's just how it streaks. So up here, this looks like a pyrite. It kind of leaves a black streak, even though pyrite is can be often confused for gold, and it's kind of got this like gold bronzy sheen on it. Then down here, this is a fluorite, and the fluorite itself, like the actual sample, is blue, but its streak is white. So the third property that we've got is luster. Luster just refers to a mineral's overall like appearance. So there are three main types of luster. There's vitreous, metallic, and earthy. So vitreous luster can be shown in this top image of the blue fluorapatite sample. So this sample is it's almost like glassy, it's very reflective, and you can see that like on some of the crystal faces, like over here and over here and over here. It reflects light. You can almost kind of like see through it. And if you were to touch it, it'd be very smooth to the touch. It would feel like you're just rubbing your fingers against like a window pane. Um, then metallic is this bottom mineral. I believe this is galena. Metallic just refers to anything that has like a metallic appearance. So I mentioned earlier that some minerals are used in like pipes and screws. It's the metallic minerals that are really prevalent in that, such as galena. And you can tell that it's got like this metallic sheen on it and it's very reflective. And then the third type is earthy, which I unfortunately don't have a picture of, but earthy just refers to anything that's going to be dull. It's usually not very reflective, and it if you were to touch it, it would kind of feel like you were rubbing like sand or dirt, some sort of like very like earthy substance. So we've got two more. The fourth one is hardness. So to do that, we refer to the Mohs hardness scale, and I found a really nice graphic of that here. So it goes from 1 to 10, with 10 being the hardest mineral, so that would be like the strongest, and then 1 would be the softest mineral. So yeah, that would be like the weakest one, the most fragile. Um, so we can test hardness in a bunch of different ways. You'll see these like side notes like fingernail, copper coin, glass, and steel. We can actually see if our fingernail scratches a mineral or if we can scratch glass with a mineral. Um, that can be an indicator of hardness. So, for example, if we had a talc sample, talc is very powdery and very when you touch it, it feels just like if you like had solidified flour. It's very powdery, it's very fragile, it's very like you could like crumble it in your hands. Um, so that when you take your fingernail, try to scratch it, you would be able to scratch talc because talc is softer than your fingernail. Your fingernail is around 2.5 on the Mohs hardness scale, whereas talc is at a 1. In contrast, diamond is the hardest mineral that we've got. And so if you try to scratch glass with a diamond, the grass would scratch because the diamond is harder. But if you took like a fluorite and tried to scratch the glass would not get scratched because fluorite is softer than the glass. Um, then our fifth and final main mineral property is cleavage slash fracture. So this refers to how the mineral essentially breaks. Minerals break in a bunch of different ways, and it's not always cut and dry. In the field, we use rock hammers, and oh, I do have a rock hammer, but I lent it to someone, so I can't present it now. But we use rock hammers, which is just kind of a regular hammer, except it's got a longer prong on the end so that you can wedge it in between rocks and try to pull them out. And we use those to lightly break some samples in order to get hand samples and also to test like cleavage and fracture. We're not trying to pulverize these things. We still want them to exist, but in order to truly test them, sometimes you got to break off a little bitty piece for yourself. So here's a couple ways that minerals break. So this sample up here is a halite, and you can see it's almost like a perfect cube. If you had a very large halite sample and you took your rock hammer to it, it would break into these cubes. Like I said earlier, no one went in and cut this into a cube shape. I mean, maybe the most that they may have done is polished it a little bit just to make it nice for the camera, but overall, this is how that mineral just naturally forms. Um, and cleavage and fracture is very dependent on bonds between atoms that make up the minerals. So a stronger bond, such as a covalent bond, would have more directions of cleavage. Covalent bond can be thought of, for anyone unfamiliar, as if you had some cash and you wanted to loan your cash to somebody. Imagine you're holding one side of the bill and then someone else is holding the other side. And so you've got a very strong grasp on it. No one can really like run and take it away because you're both holding on to it. That's a covalent bond. In contrast, biotite down here only has one direction of cleavage, and that's because it's held together by very weak bonds known as van der Waals forces. Um, if we're still running with our cash example, van der Waals forces would be like if you took your bills and you just threw them on the ground for anybody to pick up. They're not well protected. No one's holding them. They're just laying on the floor. Anyone can grab it and walk away. That's pretty much biotite. And then I've got a sample of that right here. Let's see if I can figure out how to do zoom. So biotite is very soft and, like I said, very weak. Its atomic structure is pretty much just a layer of atoms stacked on top of each other, held together by these van der Waals forces. So I can actually take my fingernail and put it in between the layers and just peel it apart. And that kind of demonstrates that this thing is not as strong as other minerals may be. And it's cool that there are these kinds of differences. Whereas this mineral, I wouldn't be able to do that, but I can still like scratch it onto a streak plate. And then it's a little difficult to see because of my blur effect, but it leaves like a reddish brown streak. And so, yeah, minerals are not always just cut and dry like these really pretty and attractive little samples. Some of them, they're all very different, and it really depends on their chemical makeup. So let me go back to my presentation. All right. And then there's also fracture. So cleavage is shown by these two samples here on the left, halite and biotite. Fracture is shown with this quartz sample. Fracture is different than cleavage because fracture is not going to have these very visible directions. Like this halite is at 3 directions at 90 degrees, And these are measurable things, and it's honestly a lot easier to see if you've got a sample right in front of you. But I believe that the biotite in the one direction is kind of the easiest to explain via this online format. Quartz, however, you can see it doesn't have these like nice crystal faces, the crystal faces being sides. It doesn't have these nice like sides, and it's not as clean cut. It looks very lumpy. It looks like someone just may have like taken a big quartz and went like this and just broke it in half. And that's fracture. There's a bunch of minerals that fracture instead of cleave, but quartz is one of them, and I feel like since quartz is a pretty famous mineral, I wanted to include that in here. So, some applications of minerals. I mentioned screws earlier. That's definitely one of them. So here, down here, we've got construction slash building. So that would be galena has a lot of lead in it. So back in the day, they used to put that in lead paint back in like older houses built between the 1880s and 1950s. A lot of those houses have lead paint on them. And then there's also fluoride, I think is pretty, or sorry, fluorite and fluorapatite. Those are pretty well used because those are used to make fluoride, which is found in your toothpaste and in your tap water, depending on where you live. One that I think may get easily overlooked is halite. We saw halite earlier. That's this mineral right here. Halite's chemical formula is NaCl, and for anyone that doesn't know, NaCl is just table salt. If you could lick this and it would just taste like salt and it's perfectly harmless. I in one of the classes that I was peer tutoring last semester, one of the students actually tested that out. I mean, I didn't tell him to, but I was like, yeah, so theoretically, you could lick this sample and it would just be salty. And I tried to emphasize that maybe don't do that, but he did it and he confirmed it tastes like salt. Another popular use is in tech as well. So lithium, graphite, and cobalt. Lithium especially, those are used to make lithium batteries, which can be found in electric vehicles. And then graphite and cobalt are found in phones and laptops. I'm not entirely sure what part they're used for specifically, but there's a bunch of minerals in our tech that we just don't really think about. And then I thought this one down here is kind of a fun fact. I just learned this within the past like couple weeks that gypsum, the mineral gypsum, is actually in sofritas from Chipotle. I didn't know that, but some minerals are edible, some minerals are definitely not. So, what does this have to do with rocks? Um, let's see. Okay. What is a rock anyways? Rocks are made of minerals. A lot of people will presume that rock and mineral are synonymous. And while in a way that's not necessarily wrong, in the geoscience world, we try to really distinguish them as different things. So we have our mineral, and as we discussed, minerals are made of elements. So I've got my little Rubik's Cube here. Imagine all of these different colors are different elements, and then just the bulk cube is your mineral. If we had 4 Rubik's Cubes, which can be articulated down here, we've got a bunch of different minerals and a bunch of different elements, and that makes up a rock. Not all rocks are going to be made of the same minerals, and not all of the minerals are going to have the same chemical structures either. They're kind of a hodgepodge of a bunch of different things, and that is how we get our rocks. They're naturally occurring and they're formed through geologic processes such as volcanic eruptions, um, plate movement, like tectonic plate movement. They're formed in oceans and along riverbeds. And there are 3 main types of rocks. There's igneous, sedimentary, and metamorphic. All right. So before we get into the three rock types, I kind of wanted to do a brief introduction to plate boundaries, just because I feel like this is kind of useful for this topic. There are three plate boundaries. There's convergent, divergent, and transform. So convergent is this first one. In convergent boundaries, land gets destroyed. This upper plate here, this will usually be a land plate. So there's, I think one of the famous examples would be um, in Japan. So Japan sits on top of a tectonic plate that's like a land plate. And then you have your ocean plate, which is the Pacific plate. And when these plates meet, they have different densities. And so one plate has to go underneath the other plate in order for them to continue moving. So we like to use a lot of different hand signs for this in the classes that we take. So if we've got our land plate up here, got our ocean plate, they're moving together, they're moving together. The ocean plate is denser than the land, which essentially means that it's heavier. So it sinks, and this is known as subduction, and it goes underneath the land plate, and that's kind of articulated by these arrows. This produces magma, it produces volcanoes. So this convergent plate boundary, there's also one on the coast of California on the west coast. So that's how we got a lot of our volcanoes over there and a lot of our some of the mountains like Mount St. Helen, that was formed because of the convergent plate boundary. Also, oh sorry, they also cause deep and or shallow earthquakes. So you might know that California's got a lot of earthquakes. Those are because, or sorry, Mexico has a lot of earthquakes, and those are caused because of the subduction zone, the convergent plate boundary. So then there's divergent plate boundaries. That's when the plates are basically moving away from each other. So they're spreading apart. We call that sea-force spread, or this creates like mid-ocean ridges. So in this, there's magma produced. There are occasional volcanoes, and sometimes there can be shallow earthquakes, although they're not as common as in the other plate boundaries, but they have happened enough where we can like classify divergent as having earthquakes. And then at transform boundaries, land is not created or destroyed. At transform boundaries, the plates just move alongside each other. And so this one can be represented, or you can think about California. The ocean plate, so that would be the Pacific plate, and then the North American plate, which is what California sits on. One plate is moving south and one plate is moving north. So they move alongside each other and kind of like this, if you can look at, if you can see my hands, um, or the arrows here on the screen, they just move alongside each other and that creates those shallow earthquakes. So we're gonna kind of speed through these three rock types. The first one is igneous. These are formed from cooling magma or lava. There are a couple different ways that we classify them, but there's intrusive igneous rocks and extrusive igneous rocks. Intrusive just means that it cools underground and it cools slowly because these rocks are formed from the solidification of magma and lava. You've got your like liquid magma, liquid lava. As it cools, it solidifies, and that's how you get your igneous rock. Extrusive just means that it cools on the surface. So, for example, granite is an intrusive rock because it cools underneath the surface of the earth um, sometimes. And then an extrusive rock would be a basalt because when volcanoes erupt, sometimes they have basaltic magma. A good example of this is in Hawaii. I believe the volcano is called Mauna Loa. When that volcano erupts, it erupts basaltic magma. So when that magma cools, because it's just laying on the surface, it forms basalt. And something that's cool is that any place with volcanic activity has igneous rocks. I mean, we talk a lot about earth science, earth and environmental science, but these processes happen in space as well. Anywhere where there's volcanoes, there are igneous rocks. So on Mars, there's a huge, huge volcano called Olympus Mons, and by huge, it is like as the size of a country. Maybe not the size of the US, a bit of a smaller country, but the size of a country. It is massive. And so, because of that, the rocks found on Mars are basalts, similar to the ones that we've got here on Earth. Same with the moon. There's evidence that the moon used to be molten rock, and so the moon is also basaltic. And here I've got a couple samples. So up here's a granite, that's probably the most famous one. And down here we've got a rhyolite. You can see that all of these igneous rocks look a little bit different. Granite, you can see these crystals, whereas rhyolite, it looks a little bit more smooth. So not all igneous rocks are going to look the same. Sedimentary rocks are made of layers of compacted sediment being like pebbles, gravel, sand, loose soils. And these are mainly formed in rivers, lakes, and oceans. So, for example, this one on the top right is a conglomerate. This one usually forms in rivers. So there's sediments on the riverbed. As the water currents pick these sediments up and like roll them down and down the river, it's kind of a snowball effect, and they just accumulate more and more material until they compact together and form a rock. Sedimentary rocks are where you're going to find fossils, and fossils are cool. So most dinosaur fossils are found in sedimentary rocks. I've got a couple pictures down here. This is a fossiliferous limestone. I'm not entirely sure what fossils these are, but I would presume that they're marine fossils just by looking at them. And then over here we've got a dinosaur fossil, and it's set in limestone as well. These rocks are a little more crumbly. We call that term friable. They're very friable, so you can kind of squish them in their hand and they'll start to crumble. And then we've got metamorphic rocks. These rocks are formed under heat and pressure and can have wavy or banded layers. That's different from the sedimentary rocks. You can see like layers here in this sandstone. Those are just layers of sand accumulated on top of each other. Whereas in metamorphic rocks, these foliated layers right here in this schist sample are made from pretty much squishing the rock so much until it squishes together and it forms these layers. So metamorphic rocks are my favorite. An example of that is eclogite, and then also marble is a metamorphic rock. It derives from limestone. But a brief kind of introduction to metamorphic rocks and plate tectonics. Eclogite and schist, which are these two down here, form at subduction zones at convergent plate boundaries. So we discussed like the ocean plate has to go underneath the land plate. This is actually a representation of that process near California. So this ocean plate, the Juan de Fuca plate, subducts underneath, and as it gets lower, the pressure increases and it gets hotter and hotter and hotter. And then the rocks that make up the plates eventually metamorphose into eclogite or into schist. For example, eclogite metamorphoses from basalt, and it grows these little red pieces, which are actually garnets. So then there's the rock cycle, and the rock cycle is not this linear as the diagram kind of makes it seem, but this is kind of the simplest way to articulate it. Rocks are all connected. They don't just kind of show up out of nowhere. They all derive from each other. So I mentioned that metamorphic rocks, such as eclogite, could derive from an igneous rock, such as basalt, and that happens through heat and pressure. So if I want to articulate that, I would want to put an arrow going from the igneous rock to the metamorphic rock, and I would write heat and pressure. Similarly, igneous rocks can turn into sedimentary rocks. If that rock is on the surface and as natural processes kind of go against it, it crumbles, and then those pieces accumulate as sedimentary rocks. So just to show that all of these things are connected with each other. So now kind of getting into fieldwork and research, which is what I'm really excited to talk about. I went to the St. Francois Mountain region last spring break, so spring break 2024, with a group of students also in my department. That class is EAES 200, and there were about 35 of us or so. and we went to study the history there. And here's a couple pictures of that, of my little field notebook and one of our stops. So we spent a week there and we studied ancient rock formations and the processes that shaped them. Missouri is actually a very unique zone for geologic history, which you may not imagine if you're thinking about like what makes Missouri cool. I don't know if you would immediately think to geoscience, but we went so that we could understand the geologic history and so we can gain exposure to field methods. This was a lot of people's first real world like experience with field work. And it's really neat to be able to go to these places and try to identify the processes. And it's very different from going just to say like, oh my God, this is so cool. It's cool either way, but through this field work, we have a better understanding of what's going on. So here's one of the things that I had to turn in as a part of my project. It's just a quick cartoon of the geologic history. And then this is me down here at the bottom of a mountain that we climbed down, and I've got some more pictures of that. So we just talked a lot about rocks. Here's kind of the applications of that knowledge. The oldest rocks that we found in Missouri were rhyolite, granite, and diabase. And all of these images here of those three rocks are pictures that I took myself. I didn't find these on the web. I've got this granite sample sitting on my bookshelf, which I think is really cool that you get to kind of take these samples and learn about them. And oh yeah, there it is, and figure out what's going on in the region based on them. There's also this cool thing called the Great Unconformity. So we discussed rock layers representing history earlier. And so imagine if you have an essay and you have your introduction, you have a body paragraph, and you have a second body paragraph. In that scenario, the great unconformity would be if someone took an eraser and just erased your introduction, and now you just have two body paragraphs and you don't know how you got there. That's what the great unconformity is. In the rock layers in Missouri, there are some missing layers, and so we just don't have any evidence of what happened there because these geologic layers represent like periods of history, and because those layers are gone, we kind of have to guess like what happened because they just got eroded away, washed away, and there's just like a gap now. Not a physical gap because, the space still gets filled regardless just because of gravity, but there's discrepancies within the rock layers found in Missouri versus rock layers found in other parts of the country. So some Paleozoic rocks that we found were sandstones, limestones, and marine fossils. Got one down here. This one's really cool in my opinion. This one is a receptaculite fossil. It's from the Ordovician era, so that would make it 440 to 490 million years old, which is actually older than the dinosaurs, which is sick. I mean, when you think of fossils, you think of like T-Rexes. This one is super, super old, and I've got that little guy right here, and in this picture you can see like really clear imprints from it. So there's also a lot of tectonic plate movement, and tectonic plates disturb the rock layers and they really do affect the landscape. And that can be shown in this image here. You've got this diagonal line, not a super clear one, but you can kind of see it dividing these top layers from these bottom layers. These top ones being a little more horizontal, whereas these bottom ones are more vertical. That's because of this tectonic plate activity, or this faulting, as we call it. It shifts the layers around and moves them around so they're not all just uniform, one stacked on top of the other. Here's some pictures of our geoscience in action. This is me. I look very confused, which I probably was at the time. And then here we've got our professor here, and then a bunch of other students. Here's one of our TAs, one of my friends, Juan. He's looking at his notebook and taking notes. We had some dog companions, Cooper and Peanut, join us for some stops on the trip. And this is probably one of the cooler days. And I think depending on time, I might have to end off on this, where we hiked down an entire mountain, which can be shown here. This is the Johnson Shut-in State Park. So on December 14th, 2005, this upper reservoir, which is just like a big pool of water, and by big I mean massive. I mean it's like 90 feet tall and it is super, super wide. It's huge. It holds billions of gallons of water. And this is a picture that I took right here standing at the road. The dam failed, like the walls failed, and so 1.5 billion gallons of water just went flooding down into this state park. All of this barren landscape that you see like this kind of cool path like shown here in this map view. This all used to be forest prior to that day in 2005, but 1.5 billion gallons of water is a lot of water, and it just washed away all of the vegetation and just exposed all of the rocks below the land. And so this doesn't happen just every day. You know, not every day does a dam fail, and we're not trying to encourage dam failures, but to make light of the fact that this happened. And luckily no one was hurt. Geologists are able to go to this place and climb down this entire mountain in order to study this landscape and figure out like, so what happened here, you know, like in geologic history, not just like what happened with this dam failure, but how did all of these geologic structures get here. And it's really cool to be able to see that. And there's a lot of like fossils exposed, and all of these different colors are from different rocks. Some of these darker colors are leftover materials from the walls of the dam itself. And you can kind of see that in these images here in the right. This is what it looked like after all of that water um, released. And so we spent 12 hours climbing down that mountain, and it was honestly super fun. So, just to wrap up, why is this work important? It's super important for geoscience and for environmental science in general. Rocks tell us stories. They tell us about past climates, about ecosystems, and about environmental changes. And you don't really think about it because, you know, a rock is a rock. You can go outside, pick up any old rock off of the street, and it's just a rock. But rocks truly are everywhere. They teach us about pyramids. I mean, the pyramids are made of limestone, and they teach us about Stonehenge and other like man-made wonders. But rocks, without rocks, we wouldn't have dinosaur fossils. We wouldn't know about dinosaurs. We wouldn't have much information about them. Um, Rocks teach us about other planets, such as the moon. I mentioned volcanic activity on Mars earlier. Without the study of geology here on Earth, we wouldn't know like what's going on Mars. It's geoscience is a very broad discipline, and it's not just going outside, picking up a rock and hitting it with a hammer, just kind of the images I've put here. Um, there's a lot of lab work, there's a lot of study, there's a lot of preparation, and there's a lot of like hands-on activities that you do in order to pretty much solve these like earth mysteries. And you can gain a deeper understanding of the earth and how it works. And through trends in geoscience, we can make predictions for the future. We can predict tsunamis and volcanic eruptions and other natural disasters. And without geologists and geoscientists, we would be at a loss of that information. And then also just for students, for us as students, doing field work is super important for being able to develop our thinking skills as scientists. I mean, like I said, for a lot of people, this was their first experience out in the field, and it's very cool to have that background knowledge from our classrooms and be able to apply that to real world scenarios, because it's not always just going to be cut and dry. Like, here's a really, really nice sample of a chert rock. You know, you're not always going to be given that. You have to go and like look for these things and really think about what you're looking at. And it's also just really nice to be able to do a career where you can be outside. I mean, not everyone is going to be suited for every career. And me personally, I don't think I'm cut out for a desk job. So doing geoscience is really cool to me because I can still make and be I can be profitable and I can make a living off of, exploring the world, which I think is really neat. And also lab research is really important too, just because this is where we actually understand the things that we've collected from the field. So a lot of paleontology is done in the lab, a lot of planetary science is done in the lab, climate science as well, just because these are controlled environments where we can either simulate geologic processes or analyze the samples that we've collected. So on that, I think I'm gonna wrap up. Not sure if there are any questions, but if there are, I think now would be the time to ask.
Okay.
So,
Hi again.
hi. So our first question says, generally, how does the difference in time it takes igneous rocks to harden or crystallize affect the resulting form and structure?
Um, so it depends on here. Let me see if I can go back to my slide. So if you have a rock that takes a longer time to cool, such as a granite per chance, you'll get a lot of different crystal faces. On that sample of granite that I had earlier in the slides, and here, I've got one right here right now, so I can just show you guys that one. So this one, you can see a bunch of different individual crystals. Each of these little dots is a crystal. So the darker ones are micas, so that could be like a biotite. The pink color comes from potassium feldspar, and then there's some little reflective pieces that are a little hard to see just because it's dark in here. But those are quartzes. And because the granite took longer to cool, because it's an intrusive rock, it cools in the earth, it um those crystals got a lot of time to really develop and make themselves present. In contrast, this one is a rhyolite. It looks very smooth and you can't really see any visible crystals. This cooled like super quickly, like a volcano erupted and then it's on the surface and then just through like, wind and the fact that the surface is colder than the under layers of the earth. This one cooled super quickly, so those crystals didn't get very much time to actually develop. So we can't actually see um, cool crystal samples as easily in this one. We would have to look at it through a microscope.
The next question says, how does the rate of cooling affect the size of crystals in igneous rock?
So similarly, when they cool slowly, I mentioned that they've got more time to develop. More time to develop essentially means that they have more time to get bigger. This granite sample has got some really big biotite fragments, and that is because that biotite had time to cool slowly and grow and grow and grow. And that's how we got these like really nice large crystal formations. Rhyolites are made out of actually pretty similar minerals to granite, such as potassium feldspar, but there's a lot of different colors of rhyolite. The one that I put in my slides was pink, so that one could be potassium feldspar. This one is a little bit more like gray, but it's got some pink bits. Those feldspars did not have very much time to cool because they cooled really quickly, so they didn't have time to grow and they didn't have time to expand, and so that's why we get these much smaller crystal sizes in the sample.
Okay. And then the next question is, how does the chemical composition of minerals affect its color?
So it depends. So depending on the chemicals, minerals will have different colors. I think so. My favorite mineral is fluorapatite, and I had put that one in my slides. Let me see if I can find it again, just because I really like that one. I think that that one's pretty cool. Um, let me see. It might take a second to get back there, but essentially fluorapatites will all have the same like chemical structure, but depending on whatever mineral, or sorry, whatever element is also added onto that, it doesn't necessarily change the mineral, it just changes what color it might be. So if a mineral has a bit of iron in it, it might have a red appearance, whereas and I think that's probably the most like famous example of that, just because when iron rusts, it turns red. Um, I'm not entirely sure off the top of my head what element would cause like a blue color, but if you've got your fluorapatite and you've got its chemical formula, depending on what element gets added onto that and bonded to it, it could turn it blue, it could turn it pink. You know, it really just depends on the what chemicals are kind of at work in making that mineral.
Okay, the next question says, what's the coolest rock you've ever discovered?
Um, I think in the field, the coolest rock that I discovered may have been that recipiculite fossil. And recipiculite is kind of a mouthful, but that is this little guy right here. Um, Here, let me let me try to pull that guy back up. All right. So that is this top one, this fossil in limestone. It's it's not a dinosaur. So, I'm not gonna, you're not gonna get featured in any like paleontology magazines by finding a recipiculite fossil, but as a student, and since this was my first time ever actually finding a fossil out in the wild that you can't just like, buy from a gift shop, it was really neat to be able to find this one and to get such like a clear imprint of its structure. And I've got it here, and you can even see it now. This organism is a coral, and so the actual organism is very like disc shaped. So this would just be like one edge of it, and you can imagine that the rest of the organism kind of just went and resided in the rocks. And so if we took samples from other parts of that area, we'd probably be able to piece together like a complete fossil, just and it would resemble this disc shape. Um, Another one that I think was really cool though is this chert rock. Chert is a sedimentary rock, and it's a little bit hard to see, but it's got these like huge like bits of minerals here. And chert being sedimentary means that it's just like an accumulation of a bunch of rocks and sediments and soils. And so it's neat to see in sedimentary rocks like how all of these things kind of jumble together, and based on appearances, they look like someone just took a bunch of stuff and just glued it to each other.
Okay, we got like 9 more questions, so we were wondering if you'd be able to like stay after a little.
Yeah, I can.
Okay, so this next question is, what determines the color of the streak of a mineral?
That is again going to be the chemical structure. So I'm going to use iron as an example again. If a mineral's got iron in it, its streak will be sort of the reddish brown. So this mineral or this sample, um, sorry, this isn't a mineral. This one's a rock. Um, you can test streak with rocks as well. And I think that this one's really cool just because it leaves a really cool color. This rock, I believe, is a shale, and it leaves a reddish brown streak because there may be some iron in the rock sample itself. And while, you can't see it, you can't really like go and try to take this iron for yourself and get little bits and pieces of it because at the end of the day, it just looks like this. There's no visible iron in there. um we can kind of make guesses that like maybe there's some iron in this particular sample. It's not always going to be like all shales have iron, but some of them do, and depending on where it formed, and we can test that by messing with the streak and the streak plates.
Next question is, what factors influence a crystal shape and how do the shapes help with identification of the crystal?
So the main factors are going to be how much space the crystals have to grow. Here, I've got a picture of that. Um, so we talked about the anhedral and euhedral formations. Here, let me go back to screen share. Yeah, we talked about this anhedral euhedral concept. So depending on space, that influences how much how big the crystals can grow. So it's almost similar to what we talked about with the igneous rocks with the granites and everything, because the granite cooled slowly, the crystals had more time to expand. With this anhedral euhedral thing, in anhedral crystals, they were grown in very tight spaces, so probably underground and really they didn't have a lot of space to actually form and kind of, reach their true big selves. So they have these like very lumpy appearances. They're not super neat. It kind of just looks like a mishmash of minerals. Whereas euhedral, because it had a lot of space to grow, so an example of that would be like in a geode. If you crack open a geode and you open it, you can see that, the inside is kind of not hollow, but there's some open space in there. There's a cavity. And so when you look at those crystals, like in like an amethyst geode, they're very square and they've got like good crystal faces. That is an example of euhedral formation. It's got space to grow because it's just like an empty cavity. And so it can form these nice like sides and edges.
Okay, so the next question is, can you explain bismuth? I'm interested in how exactly it grows.
Can I explain which one?
Bismuth?
Bismuth?
Yeah.
I think bismuth is an element. um, I'm not entirely sure about bismuth, honestly. Bismuth. Yeah, I don't know. I thought bismuth was an element, but I may be wrong about that. We don't talk about that one too much, obviously, in classes. So I am not sure if I can answer this question, honestly. But that is a good one. That's a good think outside the box question that I think I'll have to Google later. Um
Okay, the next question is, what are some classifications, groups of minerals, and what are some examples?
um I would say some classifications. The easiest classification you could make would be based on luster. So that's this glassy and metallic and earthy classification. Uh, Here, I've got a couple here. So here I've got a glassy mineral, and then let me see if I've got an earthy one. We get, as students, they give us little bags of hand samples of like minerals, and then also the three types of rocks, which is really neat. You don't have to like go outside and try to buy them or try to find them, because depending on what you're looking for, that could be really difficult. Um, so yeah, the three classifications I would say, if we're discussing luster, would be glassy minerals. So that would be like this little guy right here. This little guy actually is a halite. This is the one that I said tastes salty. I'm not going to lick it, but if you did, it would taste like table salt. Um, this one's very soft, or sorry, not soft, very smooth. And when you rub your fingers on it, kind of just feels like you're rubbing your fingers on a glass pane. It's the same with this fluorapatite over here. I do not have one of those actually. I thought I did. Um, Similarly, if you ran your thumb across that, it would feel glassy as well. That galena down there, that's like our metallic sample. I have one of those, but I'm not gonna take it out of the bag just because it's got lead in it, and then I'd have to leave and wash my hands. But essentially any other like metallic mineral. So galena is a big one just because it's very widely used in construction, but also like even the graphite in your pencil, that's a mineral. And that graphite, if you like smush a pencil lead on your fingers, it kind of has that like metallic sheen on it. That's a mineral property. Um, and then the last one that I said was kind of the main mineral um luster was earthy. And so this little guy, I don't have a picture of it in the slides. I really wish that I did. Um, but earthy just means that it's very dull and it's not as reflective of light, like how this fluorapatite is. This one's got like light reflections. Um, and then here I've got one of those actually. Here, this one, you can't really see it super well, but it's not as shiny, it's not as like smooth as like this one was. This one you can almost like see through it and it's got like these like nice crystal faces. This one is earthy, and so this mineral amongst others, you can kind of distinguish them based on that luster.
Okay, so the next question is, how can the same mineral have multiple colors?
Um, it depends on the chemical structure. It really does. I'm trying to think of another example of an element that would give you a different color, but nothing is very easily coming to mind. Um, but I guess as like a general example, like we talked about halite, the table salt one. This one is clear because it's made out of the NaCl, so that is sodium and chlorine. And, by themselves, these are not elements that you would presume to be edible, but when they come together, they make this clear mineral known as halite. And halite is pretty much always going to be clear just because it's made out of that calcium, or sorry, the NaCl. But by contrast, these fluorapatites and these fluorites, these can have a bunch of different colors. I mean, this pink one up here, this is a fluorapatite. You could maybe mistake that for a quartz, but we can distinguish those based on the way that they cleave. We talked about cleavage being like the way that a mineral breaks. Um, but that still doesn't exactly look like this blue fluorapatite sample over here. While they're the same mineral, they've got different colors, and I really can't remember which elements specifically make this one pink versus this one blue, but fluorapatite comes in a bunch of different colors. I just included these two here because I thought they were the prettiest. Um, but it also comes in like purple, yellow. I don't think it comes in green, but it could. If it does, it'd be kind of like a teal color, and then also like pink and blue. And that's just all based on different elements bonding with like the core chemical structure of the fluorapatite, which I also do not remember off of the top of my head. But the base chemical formula for all fluorapatites is going to be the same. And then there might be like one extra element that gets added onto it, and that is what will influence the color.
Okay, then we have our last question. This person wants to know, what is your favorite rock and why?
All right, my favorite rock is eclogite. Easy question. Eclogite is this little guy right here. It's a metamorphic rock, and it is the one that forms at subduction zones. So the basic answer for this is my favorite color is green, and eclogite is green, and I really enjoy that. But I also just think that it's really cool how metamorphic rocks can change over time as more pressure gets added onto them. So we talked about eclogite being derived from basalt. I do not have any pictures of basalt, but the closest thing I have is this diabase right here. These two things, basalt and diabase, are kind of similar. Um, and basalt essentially looks a lot like this diabase does. It's black, it's smooth, it's earthy, and eclogite, in comparison, looks a lot prettier in my opinion. And it's got like this green color, and then these little red fragments are garnets, which also the fact that garnet is created by this, I think is really neat. I mean, I don't have any like attachments to garnet, but I think it's nice. And I don't know, I when the plates move and as pressure and temperature gets added onto the subducting plate, so that's the one that's like going into the earth more, this like Juan de Fuca plate right here. Um, as that pressure and temperature builds, the basalt changes, it kind of conforms to its new environment and changes into eclogite. And I think that that's really neat.
Okay. Thank you so much, Jocelyn.
Yeah, no problem. I'm glad I came.
We're gonna go ahead and stop the recording and the live stream now.
Bye bye.
Bye.
Thank you so much.
Yeah.